Welcome back. Before we dive back in, let's review. Last time, we began our discussion of early astronomy by exploring the differences between Ptolemy's geocentric, or Earth-centered model, and Copernicus's heliocentric, or sun-centered model. Today, we'll discuss how we went from Copernicus's model to the model of the universe we know today. But before we get started, it's important to note that even though Ptolemy's theory was eventually proven wrong, that didn't make him a bad scientist. Just like scientists today, Ptolemy did his best to explain his observations based on the information and technology available at the time. As technology advanced, the data just naturally became more precise, giving astronomers more accurate information to work with. One man in particular who pushed the boundaries of the technology available in his time was a Danish astronomer named Tycho Brahe. A believer in the geocentric model, the one that wasn't right, Brahe built his own observatory and pushed naked-eye astronomy to its limits with his complex instruments for viewing the heavens. He then hired young mathematician Johannes Kepler to try to fit his collected data into his proposed version of the geocentric model. Although Kepler personally disagreed with the model proposed by Brahe, he jumped at the chance to be able to view Brahe's observational data, which was some of the most accurate at the time due to those complex instruments that we talked about earlier. And Kepler's patience won out. When Brahe died, Kepler inherited 20 years worth of Brahe's data, which he could now use for his own research. So Kepler abandoned the geocentric model and focused instead on trying to prove Copernicus's model of the solar system once and for all. As a result, like Copernicus, Kepler initially believed that the planets traveled in circular orbits around the sun. But as Kepler sought to justify Brahe's data, the most accurate of his time, with a circular orbit for Mars, as Copernicus had suggested, he was unsuccessful again and again and again. It was like trying to put a square peg in a round hole. It just wouldn't work. After 10 long years, Kepler began to consider the unthinkable. An ellipse. You might think of an ellipse as a stretched out circle. And you wouldn't be wrong. But technically, an ellipse is defined as the set of all points whose sum of distances from two fixed foci is constant. And I hear you asking, in English, please? So I think it's time for our next edition of Try It at Home. For this Try It at Home segment, you will need a pencil, a piece of paper, a bulletin board, 2 push pins, and a piece of string. To start, put your bulletin board down on the table, like so, and place your piece of paper on top. Next, take your 2 push pins and your piece of string. Put the string on the piece of paper and carefully put the 2 push pins through the ends of the string. Now we're ready to get started. Using your pencil, push against the string to its farthest point in all directions. When you're done, you'll have an ellipse. In this demonstration, the 2 push pins represent the foci, and the string represents the sum of distances because it remains a constant length the entire time. But why was the ellipse so important? It's just another shape, right? It was important because it represented another paradigm shift, or a change in axioms. Since the days of Pythagoras, astronomers had clung to the idea of circular orbits because they associated the heavens with the perfection of God. Why would God make funky elliptical orbits if he could make a perfect circle? Anything that strayed from the Catholic Church's model of the universe was seen as blasphemous. But the numbers worked out. In what became known as Kepler's first law of planetary motion, Kepler concluded that the planets must travel around the Sun in elliptical orbits, with the Sun located at one of the foci. And he didn't stop there. In his second law of planetary motion, Kepler discovered that the imaginary line joining a planet and the Sun sweeps out equal area in equal amounts of time. In other words, the planets didn't move at constant speeds. Finally, for his third law of planetary motion, Kepler discovered that the square of the period of a planet's revolution is proportional to the cube of its mean distance from the Sun. Let's break that down. The period of a planet's revolution refers to the amount of time it takes the planet to complete its orbit once, and the mean distance from the Sun is equal to half the distance along the major or longest axis of the ellipse. So what the equation is saying is that we can calculate either the planet's period or its mean distance from the Sun if we know the other value. It also shows that the length of the radius has a dramatic effect mathematically on the period of the planet. For example, a planet close to the Sun, like Mercury, can have a period as short as 88 days. But a planet farther away, like Saturn, can have a period of almost 30 years. All of these discoveries help to prove the legitimacy of the heliocentric model. But Kepler wasn't the only person with that goal. Around the same time, a man named Galileo Galilei was also working to prove the exact same thing. In 1609, Galileo became the first person to use a telescope to study the heavens. And as you can imagine, it led to a flood of discoveries. The most important of which, at least in this context, was his discovery of the phases of Venus. Like our moon, Galileo discovered that Venus goes through phases. And based on the way light and shadow fell on Venus during these phases, Galileo was able to determine with certainty that Venus revolved around the Sun, not around the Earth. This discovery proved the validity of the heliocentric model once and for all. To learn more about the telescope and how it revolutionized the field of astronomy, be sure to check out my next video. Until then, don't forget to reach for the stars.